Okay, parametric equations, and they can come in lots of forms. In this unit, the only thing we're going to be dealing with them in is linear equations that can also be written as parametric equations. And so what a parametric equation does is it throws time into the equation. So instead of just having an equation, for example, where y might equal something like 3x minus 1, okay? And so graphically what that would look like is you would have a line that does this. But when that line represents the path of a moving object, we don't just want to know what the path of the object is, we want to know when it was at those different locations. I mean, if the object started here at time 0, but then was here at time 1, then we know that it's actually traveling this way along the line. But if that was reversed, if we knew it was here at time 0, but here at time 1, then that changes the direction of the moving object. And we can also determine things like if two cars are going to crash, because in order for two objects to crash, not only do their paths have to cross, but they have to be at that point of intersection at the same time. So there are times when time is important to include in the situation and the equation. So, like I said, in this unit, all we're going to do is linear equations. So at time 0, so if I plug in a 0 right here and right here, then it makes this part of each equation disappear. And so what this is saying is that at time equals 0, it's starting, the moving object starting x position is A, and the y position is C. And then, if I come back here and erase this, and then, because this is attached to time, this is the rate of change, but it's just the rate of change for the x position of the moving object. And this is the rate of change for the y position of the moving object. And so that's what it says here, is B is the horizontal change, and then D is the vertical change. But they're still just linear equations. They're actually slope-intercept form. It's just that each coordinate gets its own linear equation related to time. Okay, so what that allows us to do is evaluate things like this. So we've got a radar screen, and the Titanic comes onto the radar screen, and it enters the radar screen 4 units above the bottom left corner. So what we've got is a rectangular radar screen, because it's the only way it would have a bottom left corner. And it first enters 4 units above that bottom left corner. So it first enters the radar screen at a position of 0, 4, and that's when we would start watching it. So that would be at time 0. And then it says 1 minute later, the Titanic is now at the coordinates 2, 3, so somewhere right around there. So it's at the point 2, 3 now, but we also know it's there at time equals 1. And so that tells us what direction the Titanic is moving across the radar screen. So we can watch it move from here to here, and then from here to the next position, all the way across the screen. And so what we're going to do is we're going to use that information to answer these questions. So if I want to write the parametric equations for the Titanic, that means there's going to be an equation for the x position, or the horizontal position of the ship, and one for the y position of the ship. Okay? Now remember, just a little mini version here, our ship started out here at 0, 4, and 1 minute later, so at time equals 1, it was at the point 2, 3. Okay, just a quick reminder about that. So remember, what we're doing is we're writing an equation that says, where does the x position start? Well, the x position starts at 0. And every unit of time, how far horizontally does it move? And based on the word problem on the previous slide, it moved 2 units horizontally in that first minute. So every minute it's going to move 2 units. Okay. Then the y position, we put the starting position for the y coordinate, which was 4. And you've got to be careful because 1 minute later it's moved 1 unit vertically, but it's moved 1 unit vertically down. So its vertical rate of change is -1 every minute. And that's it. They're just parametric equations. So you can now plot the Titanic's position at any given moment in time. Okay? It's also important that you note the timestamps as the Titanic moves across the screen, because the second question says, when will it leave the screen? Well, in order to determine that, you have to know where is it going to be leaving the screen, not precisely, but off what edge. So because the Titanic is moving this direction across my screen, that means that when it leaves the screen, it's going to do it on the bottom edge. Okay? And so what that means is that I know that when it leaves the screen, its y coordinate is going to be equal to 0. So if I want to know when that's going to happen, I simply take my y equation, which was 4 minus t, and I set it equal to 0. I figure out when is the y coordinate going to be 0. And so when I solve it, I get t equals 4 minutes. So that is when the Titanic will leave the radar screen. And so this point right here, I know that its y coordinate is 0, because that's the bottom edge of the screen. I know it's going to occur at a timestamp of 4. The one thing I don't know yet is what horizontal position it would be at. And so what I do is I know that at time equals 4, that's when I'm leaving the screen, and I want to know the x-coordinate. So I simply plug time equals 4 into that equation. And I now know the x-coordinate when it leaves the screen is going to be 8. Okay? So hopefully that's making sense. The next example is one where you notice that we've got one pair of parametric equations, and we've got one equation that's not in parametric form. This is the equivalent of, let's say that someone is running, and so they're moving along a path that looks like this, but they want to cross a fixed finish line. So the finish line, we don't need a timestamp on it. People aren't moving back and forth across the finish line. It's stationary. And so we have one that's parametric because we've got one object that's moving, and it's going to cross a fixed line. And so the reason that we ask you, let me change colors here. We ask you when, and then we ask you where. There's lots of ways, you guys, of answering this question, but I ask you in the order that I do because this is the easiest order to do. So if I want to know when, that means I want to solve for time. I want to know when this moving object is going to cross this line, and I want to know if it's going to cross that line, up towards the top, or if it would have crossed the line more down towards the bottom. Okay? Well, if this person is crossing this finish line, then we know that they're going to share an x and a y coordinate at some point in time. And so what that means is that this person's x position right here will have to be equal to the x coordinate on the line that it's hitting. And this person's y position will have to be equal to the y coordinate at the point on the line where it's crossing. And so what that means is that we can substitute. If those things have to be equal, because they have to be intersecting each other, then we can substitute. The x coordinate on that line will have to be equal to the x position of the moving person, and the y coordinate on that line will have to be equal to the y position of the moving person. And so what we've created is we've created an equation where we've only got one unknown. It's just time. So what I want you guys to do is I want you to take the next step or two. I want you to simplify that equation a little bit so that we can solve it. I'm sorry, I forgot to remind you to pause the video, so hopefully you paused it and you took a second to do your simplifying a little bit. So hopefully what you did was you distributed the 2. So you got 6 plus 2t. And then you need to make sure you distribute that minus sign, so it becomes plus 1 minus 3t. And it's equal to negative 3. And so when we combine our like terms, we end up with 7 minus t is equal to negative 3. And so ultimately we end up with t is equal to 10. Now they didn't give us a unit in time, but we're going to assume that, if we're using the analogy of the runner crossing the finish line, that it would have been in seconds. But at time equals 10, that is when the moving object crosses the finish line or the fixed line. Okay? And once we know when, finding where is really easy, because remember, we have two equations that will tell us the x and the y position at any given moment in time. So if I took my x equation and I plugged in the time I just got, then I know the x position is 13. And if I take the y equation and plug in the time that I just got, then I know that at time 10 the y position is 29. So at time 10, at the point 1329, is when and where the moving object crosses the fixed line. Okay? There's two final types of problems. The first is when there are times where you don't care about time, you just want to know the path of the moving object, then you can eliminate time from the equation. So what you do is you rearrange the x equation to get t by itself, and then you simply plug it into the y equation. And that will eliminate time from the equation so that all you're doing is just x's and y's. So if I did that here, if I took this x equation right here, and I simply subtracted 3, I would have an equation that says time is equal to x minus 3. And now I can take that and I can plug it in right there for time. And so my y equation is now negative 1 plus 3, and then time gets replaced with x minus 3. Okay, now depending on the form of the equation you're asked for, you don't necessarily need to rearrange that equation. This right here is actually point-slope form. And we love point-slope form. I've made you work with it before this year. Your calculus teachers love point-slope form. It's what they use for linearization and things like that. But let's say hypothetically that I'd asked you for a slope-intercept form. So you would want to go ahead and distribute. So you would get 3x minus 9, and so you would end up with y equals 3x minus 10. There's your slope-intercept form. Keep in mind, I could also ask you for standard form, big hint. And just keep in mind, standard form is just ax plus by equals c. So you would need x and y on the same side. Usually we don't lead with negatives, so you would need to make sure that you have no negative for the a right here, and that you have all integers. So for this equation that wouldn't be hard. We'll practice ones with fractions and that kind of stuff in it later. And the final type of problem is if you have a moving object and you want to know if it ever goes through a certain point, then if a moving object is going to go through some point in space, then that means that it's going to be at that point at some moment in time. And so what that means is that it has to have that x-coordinate at the same time that it's got that y-coordinate. Okay, let's say that, hypothetically, that we figured out that our moving object hit that x-coordinate at 5, but it didn't hit that y-coordinate until 9. Well, that means that you're not ever going to hit that point in space because you're not at that point, meaning you have that x and that y at the same time. And so there's two ways to go about figuring this out. Okay? And both ways use the same first step. The first step is to figure out when does my moving object hit this x-coordinate. Okay? So I'm going to do that. I'm going to figure out when is my x equation equal to 13. When do I hit that x-coordinate? So I subtract the 3 and I divide by 5. And so I know that at time equals 2, I have the correct x-coordinate. Okay? Now, here's where you have the two options. Option 1 is to repeat the process, but figure out when is the y-coordinate equal to that. So that's option 1. So I'm going to show that to you. So I'm going to take my y equation and I'm going to set it equal to -4 and figure out when is y equal to -4. So I add the 8 to move it over, and then I divide and I get -2. And so what that's telling me is that I'll have the correct x-coordinate 2 seconds from now, but I had the correct y-coordinate 2 seconds ago. And so the answer here would be no. I don't ever go through that point in space. Okay? Now my second option is I know that I have the correct x-coordinate at that time. So what I could figure out is what is my y-coordinate at that time. So instead of coming over here and solving again, what I could do is I could evaluate instead. I know that at time 2, that's when I have the correct x. So I plug that into my y equation and I figure out at time 2, I'm at the y-coordinate -12. So I'm not at -4 like I'm supposed to be. Either way, your conclusion is the same. No, you don't ever go through that point in space. Okay? So now, really quickly, you try number 2. Figure out if that moving object ever goes through that point in space, and if so, when. So go ahead and pause. Okay, so hopefully what you figured out is that you have the correct x-coordinate. You're here at time equals 4. And then either using method 1 or method 2, you figured out that at that time you were also at the correct y-coordinate. So yes, you do go through that point in space, and you do it at time equals 4, whatever, 4 minutes, 4 seconds. Okay, so that's it for parametric equations. And believe it or not, we only have one more day of notes in this unit because it's all linear equations. So we're going to be doing a lot of in-class practice. So hopefully that helps everybody.